Good morning, I'm Technical Sergeant McCusker. I am the Block 2 instructor. This is Unit 3 Alpha. We are going to be going over 3 Alpha, which is to identify the relationships of basic facts and state general principles about the functions of the HF transceiver module. This is the guts of the radio here, guys. That's what we're going to be going over. As always, your minimum is at 73% on the block test. That means you need to get 11 out of the 15 questions right. But as Sergeant Gaston said yesterday, he wants everybody to get at least a what?
A minimum of 3 questions failed.
Yeah, so an 80%. He doesn't want anything below that because he doesn't want to have to counsel an AEL. There are many different HF radios in our career field. Each may be slightly different, but the basics are the same. Understanding the following theory and block diagrams will give you a better understanding of how these HF radios function. What does this mean to y'all? Aaron Johnson, what does this mean to you?
It means to me that the radios may do different things, but at its core, they have the same structure, I guess.
Yeah, absolutely. They have the same structure at its core. I like that. That's very good. That's a great way to put it. Why do you think we might not understand the guts of the radio? I mean, I know we keep telling y'all that you're not maintainers anymore, and that's what we were when I came in. We had the maintenance badge on. We used to wear the little eagle with the little bomb in its hand. We don't wear that anymore, and a lot of the times we tell you guys that we do swaptronics, but what do you think would be helpful if you understood the guts of the radio?
Probably just general troubleshooting. It might be beneficial to understand the inside and out of the radio, or if there's not a maintainer around and we need to fix something.
Absolutely, yeah. You could be in a remote location. That's a great example right there. Yeah, absolutely. And just kind of understanding the stuff in addition will also help you when you go to send the radio back to these Harris guys. It'll help you identify and pinpoint the problem much faster, which will allow you to get your radio back faster in theory. So we talked about this hub battery yesterday. Y'all should be familiar with that. We're going to talk about assemblies today. I'm going to give you guys a little overview on what the difference between an assembly and a subassembly is, because if you're looking at your circuits and diagrams sitting in front of you, this may be a little bit confusing. And we'll go pretty in depth into all this today. I'll slow down, take my time, teach you guys some tips of the trade I've learned that have helped with kind of memorizing and reviewing these C's and D's. So our transmit signal flow is what we're going to talk about first. It's going to be clear voice. That's that unencrypted voice coming through, that data. And then we're going to talk about encryption. And we're going to talk about receive signal flow, because we don't just shoot signals off into the ionosphere and hope they hit something. We have an intended target. Our intended target has the received signal, hopefully, and they will receive our transmissions. So they're also going to be doing clear voice data and encryption on their side to match up with whatever we have on our side. All right, we'll talk about theory of operations first. I'm going to give you guys a little bit of a clarification at first on this subassembly, assembly mumbo jumbo that they're talking about. I'm going to flash forward here a little bit. When we look at this diagram here, enhance, 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 enhance. When we look at this diagram here, you guys may notice that it says A2 here. And you may notice, in addition, that it also says A2, A1 right here. This is the difference here between an assembly and a subassembly. A subassembly is kind of like when you're going to kindergarten and you're cutting out the little face to put on a popsicle stick for your parents for Christmas. You know, you don't have anything else to make them, so they usually make you make something for your parents. You're kind of cutting in those dotted lines, and then what's in the product on the inside is what you're going to hand them, or what you're going to discuss. That's what a subassembly is. It only cares about what's happening inside of here, the modem, the digital intermediate frequency application specific integrated circuit, our controlled data signal processor, our control field programmable gate array. That's all it cares about right here. It does not care about anything else that's going on the outside. Whereas when we talk about the assembly, this is all A2, everything inside here. So we care about a little bit of what everything's doing. It's kind of like Bob Ross up there saying he's gonna paint a little happy cloud up here and a little tree there, and he's just doing those broad strokes, getting out the point of this is what the A2 does itself, but not going into the specifics necessarily. We don't really care that the ALC is here or the AIC or VDP. We don't care about that as much. We just kind of want to give you a general overview of what these things do. Make sense?
Yes, sir.
Clear as mud for anybody? Was that Bob Ross reference a little too old for anybody?
No, he's cool again.
Oh, he's cool again? Okay, that's good. He was in the Air Force. All right. A2 is a designator for the entire assembly. We just went over this. This assembly has many submodules. For example, A2A1, A2A4, and A2A5 as examples. These submodules each have a separate job or function in the radio. Talk about the theory of operations. Like I told you guys, this is assemblies. When we talk about these, I want you guys to go to table 3-1 in your Impedance panel right now. So I'll give you guys a couple seconds to get there. Let me know when you get there. Let's see some thumbs up in the chat here or something. I'm monitoring the chat on my phone, so hopefully it doesn't crash like it did the other night. All right, you all there? Aaron Bull, Aaron Johnson, Aaron Faber, James Smith.
Here, sir.
All right, everybody's there? Perfect. One of the reasons I want you guys to follow along with this is because remember, come test day, what do you get?
You get the access to the TOs?
Yeah, you get the TOs. You get the TOs and you get the circuits and diagrams. You don't get these slides. So this is a view as if we were to open up the radio ourselves and actually pull it apart piece by piece. You guys are not going to do this because there's a whole bunch of bad things that are going to happen. You have to be in a secure environment, first of all, in order to even do this. So please don't just pull apart the radio. Even if you are level 2 certified by Harris, I had an airman one time who was level 2 certified by Harris and he wanted to start taking stuff apart and I had to yell at him. So please don't do that. So A1 chassis, that's the A1, it protects the A2 lower chassis. I like to call this thing the turtle shell. As you guys may have noticed yesterday when you were in class, what color was the radio?
Green.
It was green. What does a turtle shell do for a turtle?
It protects everything on the inside.
It protects everything on the inside. What do you think the A1 chassis is doing?
Same thing.
Yeah, that's a turtle shell. I had a guy from Alabama in my class one time. That's what he told me. He said, "Sergeant McCusker, that's like a turtle shell," and it just like stuck with me forever. I thought it was great. So as the upper chassis assembly, all these things are contained in here. It contains the A2, the A3. It has the A4 in there, but as you can see, the A4 is the rear panel, so you can pull it out. They're talking about the internal side of the A4 is in there. Provides a mounting structure for the front panel interface connectors, the A5 KDU. This can actually come off. That's what it's talking about. When we look at this, this is our A2 and our A3. So your A3 is this part up here, and then the A2 is actually beneath it, making it the lower. So A2 is processing voice and data signals. It supervises control functions for the entire radio. It also contains the the encryption assembly. So all of our CCI magic that we were talking about that makes this radio so expensive happens in the A2. A3, it contains the analog RF sections of the radio. It's got the receiver, exciter, filters, power amplifier, tuning circuits, analog output at 240 kilohertz. That's our first IF. Then we go to A4. That's our rear panel assembly. Rear panel assembly contains the radio power supply, provides the interface connector to the batteries, the hub, protects the memory, all that good stuff. What is the hub battery? We keep talking about this thing. We talked about it yesterday. What is it?
The hold-up battery.
Whoa.
Oh, it's on the slide too. It keeps the radio from zeroizing if you disconnect power.
It does not keep the radio from zeroizing.
It's a memory retention battery.
Thank you.
So
it's like a CMOS battery in your computer. What does it hold? How many presets and how many channels? How many system presets and how many channels? If I don't get an answer, I assume you guys aren't looking it up in your operations manual. So it's 75 system presets and 200 channels. And that's available in table 1-1 in your operations manual, your commercial operations manual. So when we talk about this A4 rear panel assembly, this is where the hub is actually housed, that thing that's used for protecting the memory when the radio is off. If you zeroize the radio, though, remember that it wipes everything. It doesn't care if you have a hub battery in there or not. It's going to wipe everything. So don't think that your hub battery is going to save your progress, basically. It's like getting halfway through an old PS2 game and then realizing you didn't have your memory card plugged in or your memory card was full.
Oh, I wasn't talking about like if you turned it over to like the zeroize function on the switch. I was talking like if you like disconnected the power and there was like no hold it battery in there, it wouldn't retain what you just did.
Oh, okay. Understandable. Yeah, that's 100% true. Absolutely.
Sorry, I think I don't. Yeah, I didn't mean it the way I think you thought that I meant it.
Well, that's good that I didn't think that you thought that I meant it that way, that you think that we thought about it. Outstanding. You guys are killing me this morning. I love it. All right, J10, J11, that's our battery connectors. We don't need to use a dead horse to beat a stick there. We can see that. These are J10, J11. We went over those yesterday in 1 Bravo, our controls and indicator section. This is the hub battery. When you guys pull it out, it's actually like a tiny little green and white battery. I'm going to see if I can find a picture of one for you guys today. I'll just post it in the Discord chat for y'all. These things are a pain in the butt to get back on once they come off. Just warning y'all now. So A5 is our KDU. Another name for the KDU is the MMI, the man-machine interface. That's another name for this thing here because you are the men and women and you interface with the radio, the front panel. So is everybody good for intermediate maintenance manual page 3.3.1.1? If not, please go get there because this next section is going to take a little bit. This is going to be the meat and potatoes of our discussion this morning. No problem.
On the page.
You're on the page. Perfect. Okay, if everybody's there, this is just kind of some stuff that I'm going to go through. I'll have my little things I throw in and out of there. If you're following along in the circuits and diagrams, the handout as well, that's good. If you're following along with the TO, that's even better because you get your TO on test day. And there may be some things that are in the TO that are not on the slides. Now, when we come in through J1, we come in as what type of format, what type of modulation? Is it analog or is it digital format?
Analog.
Analog. It's like you guys knew I was going to ask you that question. It's amazing. Somebody give that away.
No, I've just been here before.
You've been here before.
Yeah, I was here last class.
Oh, I didn't know that. Oh, okay. All right, so yeah, J1 audio comes in as analog. And then it goes to the ALC, the automatic level control. That's what ALC stands for. I know it looks like A1C or something else, or even the thing next to it looks like it says A1C or a rank, but it's not. That's a chip. So the ALC's job is to adjust those varying voice levels as they come into the radio. As your voice is low or high, it will keep that gain level constant as it goes through the radio, because it doesn't want to mess up any of the sensitive circuitry that's about to go through. From the ALC, we go to the AIC. That's the analog interface chip. And when I say chip, I don't mean chip like munching on a chip. I mean chip as in the tiny little thing inside of a computer or inside of a radio. It's a little processing chip. And it's going to take that analog and turn it into digital. Why do you guys think we're going to turn it into a digital format?
So it can be encrypted or decrypted as needed.
Okay, that's part of it.
It's easier to put through the subassembly.
Yeah, it's easier to push through the radio. That's why. It's easier to manipulate digital information in this portion of the radio than it would be to manipulate analog information. So the radio can process it a lot better. That's why we're changing it. So once we've changed it to that digital format, we need to clean it up a little bit. So this VDP here, the voice data processor, is going to take that audio and it's going to clean it up and it's going to represent your original sounding voice a lot better. I know the first day, I think it was your guys' class, that we had someone who was having mic issues. Was that your class?
Yes, it was.
What did you do to fix that?
If I remember, Brooks had to change his microphone settings.
Okay, cool. So his voice kind of got cleaned up and sounded a little better, so I was kind of equating this to that, what you guys did there. At least I assume that's what he sounds like. He doesn't sound like a helium eating a balloon all the time, I
Generally,
assume.
no.
Yeah. Okay, that's good to know. Good. So then we go to this thing called the PTF PGA. That's the plain text field programmable gate array, and it directs that data and voice coming in. I like to call this the traffic cop. Why do you guys think I want to call it a traffic cop?
Because it directs traffic flow.
It directs traffic flow. If it's in encrypted mode, it's going to go up here to CSC, Citadel Cover. If it's also in another encrypted format, CT, ciphertext, it's going to come up here and go through the A2, A5. It's just going to tell it where to go. That's all it's doing. It's just like a cop standing out there saying, nope, don't go that way. Next, we're going to go to the A2, A1. But before we move on to that, does anybody have any questions about anything that's happening in A2, A4?
No, sir.
Great. If there's no questions, then we'll move on. CFPGA is next. That's the control field programmable gate array. And if you read in y'all's text in 3.3.1.1 in that TO, it's literally just going to tell you, unless it's data, it's just going to push it on through. And if it was data, it's going to come up here and go through this modem right here. Does anybody know what modem stands for? That's your modulator demodulator. That's what a modem is. Mind's blown if you didn't know that. And then from there we go to the CDSP. I know it looks like it says ODSP. To me, I think of that Halo game, ODST, whenever I look at this thing, because that's what it looks like to me on the slide. But all this is doing is it pushes it through again. From there, we're going to push that information through, and we're going to do what's called the digital modulation in the radio. So the digital modulation inside the radio is going to happen in this A2A1 subassembly. Specifically, it's going to happen in the digital intermediate frequency application specific integrated circuit. No, you do not need to memorize that name I just said, because you all have a what?
A TO.
Y'all have a TO. Perfect. So we can look at this. It says it modulates and digital to analog conversion take place here. The first IF is the 240 kilohertz. It is digitally modulated to produce the correct modulated waveform. So this is our first IF happening here. It's getting created here. However, it's not getting pushed out yet in the analog format that we need it in. We need it in this analog format because it's about to go through the A3 section of the radio, and that's, as it said before in the subassemblies and assembly breakdown, is the analog RF section of the radio. And there's a specific reason it does have to be this 240 kilohertz number here. And I'll explain that in a little bit. So what do you guys think D/A stands for?
Digital to analog.
Perfect. What do you think A/D would stand for?
Analog to digital.
Analog to digital.
Perfect. Guess what's going to happen when we come back through the radio and receive a little bit later?
It's going to get moved back from analog to digital.
Absolutely. You are 100% correct. I apologize if y'all can hear that train outside my window. From there, we go to the A3. As I said, that's the analog RF sections of the radio. This is where we're really going to do some manipulation with the signal here, is the signal strength, the level of it, and things like that. We're going to kind of put our frequency in that we programmed from the front of the radio, and we're going to convert that analog into an RF frequency. So there's a lot going on here in the A3 section. Specifically the A3A1, there's a ton that's going on in the radio. What is an attenuator? That's my first question I always like to ask. Do you guys know what an attenuator does?
No, sir.
Okay, perfect. An attenuator will drop the overall signal power or signal level down by whatever number is associated with it, or whatever you need that signal strength level to be at. Specifically in this radio, the AMPRC 150, it's going to drop it down by 13 dB, meaning we're going to take away 13 decibels of gain from our overall signal level. So that's like taking away some power from it. If you guys didn't know this, when you take away 3 dB in any system, you half the amount of power you have. So we're halving it a whole bunch here. Now, the same can be said about adding 3 dB. If you half when you take away 3, what do you think when you add 3 happens?
It doubles.
Yeah, you double it. You double your power. Very good. Absolutely outstanding. So the reason we're doing this, though, is because we're about to go through some filters, a mixer, some very sensitive equipment in here, and anytime you go through some little sensitive components, you have to be very precise with the amount of signal level you're sending through, because you can cause some damage to these systems over time if you do not. That's why everything's dropping this down. And remember, it shouldn't really be that high anyway, because we only have 240 kilohertz that's getting pushed through here right now. That's it. So it should not be that high. I really believe this is just in here before when you hook up that exciter bypass path thing down here, and we use that power amp, because that power amp can push upwards to 250 to 300 some watts through it, and they really want to be careful with that coming through here. Now from here, our attenuator, we go to the LPF. It's a low pass filter. Anything less than 1 megahertz is going to pass unchanged to the next stage. It gets rid of noise. What is noise?
Like white noise.
Yeah,
Non.
okay. It's things you don't want in your signal, right?
Right, like squelch and.
Yeah, like squelch. Well, not necessarily squelch, but yeah, it's things like you don't want in your signal. Squelch refers to a floor or thing that you set. The squelch level can get rid of noise, so squelch is more used to get rid of noise.
Okay.
We're not going to get too into that because I don't want you guys to get too confused with that. I can explain that after class if you want.
Okay.
Yeah, I have no problem doing that. So when we come to this here, this is our mixer, or what is another word for mixing that we learned in this block? Starts with an H, ends with heterodyning.
Heterodyning.
Heterodyning, very good. Yeah, because we're taking our sum, our difference, and our two original frequencies and mixing them through here to get our output of 140.4. So we're taking this 240 kilohertz that we had, that first IF, so this is why right here, guys, the number has to be 240 kilohertz. We're taking that 240 kilohertz, we're adding it to 140.16 megahertz, which if you do the math here, 140.16 plus 0.240 is equal to 140.4. This is why this number has to be that way. And even further so, it's going to have to be that way because there's another thing that's going to happen over here with this guy. So let's explain this local oscillator thing down here. This is what's known as an injection frequency, as it says right here, and it uses something called phase lock looping in order to give you that specific frequency or give you these two frequencies right here. What that does is, in this instance up here, this VCO will generate this 140.16 megahertz. It's going to send it back through this PLL to lock it into the signal. So as it's locking it in, it's going to send it back up, and then it's going to go into the mixer and allow for these two signals to mix and give you the output. Make sense?
Yes, sir.
Cool. Anybody know what this is? I just like to ask that question. No, it's not an electrical fork. Okay, that's your ground. That's what that is.
Oh, dang it, I couldn't get my mic to work. I was about to say that.
That's okay. All right, so now that we have all our signals mixed, we got to talk about some other things in here. We have this BPF thing that's a band pass filter. It's like going backstage at a concert. If you have a backstage pass, they'll let you backstage. If you do not, they're not going to let you back there. In this instance, if it's not 140.4 megahertz with a 40 kilohertz bandwidth there, it's not going to come through. It won't let it through. That's it. Period. So this 144 megahertz IF is amplified and filtered through 40 kilohertz bandpass filter, and then amplified before being attenuated by a digital attenuator. Why do you guys think all this amplification is happening in here? What did I just tell you about attenuators and mixers? What are they doing to that signal level?
Well, the attenuators drop the signal level.
Yep, they sure do. So attenuators will drop the signal level, just like filters are going to kind of lower it a little bit because they're filtering out those things they don't want in the signal. Your oscillators here are going to kind of mess with the signal a little bit when it gets mixed. So as you go through this mixer, so you naturally would probably need some more amplification before you send it through that bandpass filter, because even if it was the right signal level, it might not get through there if it wasn't amplified enough. Make sense? All right, so
Yes,
from there we go to this digital attenuator thing. That is part of what's known as TGC, transmit gain control, or as I like to always make the joke, it's TGC, not THC, the stuff that's legal in Washington State. This holds the power at the antenna constant while variable voice levels are coming in. So as those voice levels, remember from the ALC, that automatic level control, come through and fluctuate and try to be held constant, this is just kind of another thing put in place to make sure they stay constant as they get through here. Make sense?
yes, sir.
Cool. From there, we go to the second part of the mixer here, which is responsible for your entire frequency range of the radio. Now, if somebody did 142 minus 140.4, they would find that they get the number 1.6. If they did 200.399, like it's showing here, minus 140.4, you would find that you get 59.99999. What is that the range of?
Very high frequency.
Not VHF. What is this the range for? What have we been talking about this entire class? What's the thing you went and programmed?
That's the frequency range of the radio.
That's the frequency range of the radio. That's the entire frequency range of the radio. Does that kind of make sense to everybody a little bit more now? Why these things have to be so precise?
Yes, sir. It makes more sense now.
Okay. I know that today is like pretty heavy for some people, but I think this does kind of explain a little bit better for y'all. Perfect. From there, if everything was normal and we weren't hooked up to an external power amplifier, we would just come out through the top part here. However, if we were hooked up to an external power amplifier, we would have to reduce that signal level again by another 23 dB in addition to this 13 dB we already reduced it by, because you're pushing so much power, like I told you guys, through the radio. And also it's going to bypass all of this stuff here. Then we have this final PA here to give our last push of power through, but note that it is not used. This will not be used when you have an external PA hooked on. So that's, again, part of that. Then we go through some filters here. We're going to use 2 out of our 9 filters we have available to us. Yes, I said 9. So you see HF1 to HF8. However, this BCI down here counts as a filter, so that's 9 total. In a second here, we're going to blow this diagram up and you guys are going to see this, but I need everybody to go to table 3-2 so I can ask you all a question. Oh, are all 6 of you in here now?
Yes, sir. I'm sorry I was late. I assumed the meeting was at 09,
You're
and
fine.
I wasn't in
You're
the door.
fine. That was on me. You're fine. I'll let everybody know you're here.
What table is that again, sir?
3-2 in your intermediate maintenance manual.
I'm ready.
You ready? Nice. I like all these thumbs up. That's sweet. You're fine, Aaron Burr, but that was on me. I asked them because you guys are already in here, and I figured you had nothing to do, and we could finish a little earlier.
Yes, sir.
You can listen to the video later if you like. I'll post it in the chat for y'all so you can get those parts you missed, or we can go over it after the class is over. I'll sit back and go over it with you.
Thank you, sir.
No problem. That's what I'm here for. So everybody's on table 3-2. Y'all ready for my question?
Yes, sir.
Perfect. So if I have a frequency of 27 megahertz, which HF high filter am I going to use?
Band 7.
Band 7. Very good. As you guys see, like you just said here, this is the band 7. This is what your table looks like. Outstanding. Very good. Let's talk about this BCI filter real fast. This is for that AME mode that we talked about the other day. Do you guys remember talking about AME mode when we talked about modes of the radio on day 1? I know this was many moons ago. I'm asking you to remember.
Yes, sir.
What does AME mode do? Airman Burba.
I don't exactly remember what it does, but I remember us talking about it.
Okay, so AME mode stands for amplitude modulation equivalent, and its job is to reinsert a little tiny portion of that carrier back into the radio signal so that you can talk to AM citizen band radios. That's what it's for. You'll get there. Very good, though. Remember, all of this information is in y'all's TO. Can't use that dead horse to beat a stick enough. Now, once we're through all our filters here, which we also call our post-selector network, because it happens at the end of our radio section here in circuits and diagrams, not before, otherwise we would call it a pre-selector network, we go through something called a high-level limiter. The high-level limiter, I know it doesn't have a little thing on here for it, but all it's doing is limiting those high levels from getting back into the radio. It's going to actually shut the radio down if you get a bad VISWAR mismatch, so that these things behind it, this PA, this filters don't pop and break when high-level signals come through it on the way in, if you have bad components in the radio, or if you have a VISWAR mismatch. Now, directional coupler here is going to do a couple things, and that wasn't a funny joke there, but the VISWAR data is produced to tune the antenna coupler and provide information to the TGC circuits, those transmit gain control circuits, and also sends bias control signals to the final amplifier. This thing is going to ensure that you have enough power being pushed from this final PA here. That's why it shows this bias control, to get that signal out, that frequency that you guys programmed on the front of the radio. That's what it's doing. So it needs to send a signal back here so this knows how much power to push through for the specific signal that you have coming in. And then from there, it's going to take all that VISWAR data it collects, and it's going to pass it on to the antenna coupler. The antenna coupler is going to do something called impedance matching. Do you all know what impedance matching is?
Matching impedance.
Thank you. Matching impedance. Impedance is resistance, yes. Your total resistance. So it's going to match your total amount of resistance. That's what it's doing. And the couple control tune data is used to switch the various inductor and capacitor elements into and out of the circuit until a good impedance match is found. We don't want an impedance mismatch because that's going to cause VISWAR errors. You're going to end up with like a 3-to-1 ratio or 2-to-1 ratio, and over time that's going to make things go bad. It's going to make your antenna go bad. It can make your cabling go bad. It can make some of those components inside the radio go bad if you have it on long enough. Just lots of bad things are going to happen. Now, with a lot of newer radios, they have this high-level peak limiter thing, like I was telling you guys, that will stop that from breaking these sensitive components in the radio, but it's not going to stop it from breaking the antenna over time. Things just go bad, too, by nature, after a long period of time. No matter how many PMIs you do on them, it doesn't matter. Things are just going to go bad over time. That's just how technology works. I'm sure you guys have noticed that with computers. You buy probably a new computer or a new phone every couple of years because something happens with your old one. Typically. Unless you're like Mr. Rodal and you have a flip phone still. That man still rocks a flip phone. Alright, so the antenna coupler, the A3, A5, it does this impedance matching thing we were talking about, which takes place between the radio and the antenna. It's fed to the J7 antenna connector. That's the 50 ohmic connector on the front of the radio where you guys plug in either the OE505 or the NIVIS, as we talked about in class earlier. What's another name for the OE505 antenna?
Is that the whip antenna?
That's the whip antenna. Outstanding. It compensates by switching between these capacitors and inductors, which you guys can see here. See the inductors and capacitors? No, I said inductor, not conductor, like George Carlin and Thomas the Tank Engine. Inductor. And then what are these things again down here?
That's grounding.
That's grounding. Very good. Why do you think we might have some grounding before it goes out to the antenna?
That way no one gets electrocuted and everything flows fine.
Perfect. Very good. That's why you might need some of that stuff. So as I just told you guys, this gives the radio set the option to connect the OE505 whip antenna or any number of other antennas chosen to meet your mission requirements. You guys will learn more about different types of antennas as you go further into the course. Specifically, Block 4, you're going to learn a lot more about antenna types and antenna theory. So hopefully you enjoy that. I enjoyed that portion of the course when I came through. So let's ask some questions here. What is TGC, Aaron Burba?
I assume it's not a trading card game.
It's not a trading card game. Yeah. It's not Pokemon TGC or TCG. Yeah. Nope. Anybody remember what TGC is? I said it's that stuff that's legal in Washington State. I mean, you know what I'm talking about.
Is it time? Is the first thing time?
Negative.
Transit gain control.
It's transmit gain control. It holds the power at the antenna constant while varying voice levels come in. Here's your answer right here. You guys see this? It happens at the digital attenuators. All right, very good.
Yes, sir.
Why is voice converted to digital? That's in the A2, A4 section, the first part we come in the radio. So after we've adjusted our varying voice level coming in, we go into that AIC. This is where that happens. That thing we just talked about.
Because it's easier to manipulate.
It's easier to manipulate. Yep, it's easier to manipulate. Where is our second IF located? So our first IF was located right after the A2, A1, and it was 240 kilohertz. Where is the second IF located? Y'all see what I highlighted?
Yes, sir.
Yes, sir.
So where is the second IF located? I need an answer.
Is it
In the A3A1.
Thank you,
But
the A3A1.
I wasn't looking at the screen. I was trying to look on my piece of paper, and it didn't even show that on my piece of paper.
It shouldn't show this writing on your piece of paper, but it should show the 140.4 megahertz IF right here after the mixer. On your diagram.
The only place that it shows another IF is after the digital attenuator.
Okay. That could be just because the paper's getting old or the copy he gave you guys is old, but if you want to write this down, this is where it happens if you guys want to put this on your paper.
Okay, I'm going to go and write that down real fast.
That's fine. I'll leave that up for a second. Is anybody confused on anything so far? I know we've gone over a lot, and the second portion of this is going to go a lot faster because you guys kind of have a grasp on how the transmit portion goes already. And most of these things, when we go back over this, are not really going to change their job.
I am extremely confused, but that's all because I wasn't here.
It's because you what?
It's just because I wasn't here for like the beginning part of it.
Okay, we'll get you caught up. Don't worry. I'll get you caught up.
All right, I'm good to go.
Okay. So our exciter bypass path happens down here. Guess all that. Don't need to go over that again. So we're not going to do this question right now. We'll do that at probably the very end. Where does the digital modulation portion take place in the radio? What assembly and what subassembly? Give me both.
It's A3 assembly, and then the A3A1 subassembly.
Incorrect.
Is it the A2 lower assembly?
It's the A2 lower chassis assembly. Which subassembly?
A2A1?
A2A1, outstanding. Specifically in the DIF ASIC, the Digital Intermediate Frequency Application Specific Integrated Circuit. Any questions on clear voice transmit so far? Nope. Then we'll press. A1 to A2A4, that's what we talked about. It has the analog to digitized audio happening there. A2A1 is responsible for our digital modulation and our digital to analog conversion. A3A1, that's our start of our analog RF section of the radio. For A3, it's the IF to final RF KDU frequency. So if you guys noted, when it says carrier frequency after that second mixer in there, it's actually an RF frequency from that point on. And then A3A2, that's the final PA, that final push of power happening, unless you have an external PA connected. And then we have our post-selector filtering, our VisWAR data, and our impedance matching. Next, we're going to talk about encryption and how that flows through the radio. But before we do that, we can talk about data because it happens real quickly right here. If you guys will notice, nothing is really different except that data comes in through J3. Now, my biggest question to you is data coming in as digital or analog? Which format?
Would it be analog?
Incorrect. Remember when you're passing back and forth ones and zeros to each other using like the CPA, or we're using TacChat, for example. That's the tactical chat software that you can use. It's kind of like old school instant messenger. And we can use that with this radio. It's already in a digital format when it comes in. That's why we don't need things like the ALC, AIC, and VDP up here as we do for the analog to digital conversion and the cleaning up of the audio. Make sense?
Yes, sir.
Perfect. So J3 digital data comes in down here, or digital information. It's going to go to the DTE, that's the data terminal equipment. It's going to hook into like a DS101 or DS102 hookup. It's going to go to the PTF PGA from there. And what is the PTF PGA again? Anybody? PTF PGA.
The traffic dude.
The traffic dude. That's your traffic dude, your traffic cop. He's going to route the traffic, either CC or CT. From there, we go to the CFPGA, that's Control Field Programmable Gate Array. Since it is data this time, it will go through the modem and get modulated on our transmit side. When it comes back through on the receive side, it'll get demodulated, the second part of the word modem. From there, we go to the CDSP, the Control Data Signal Processor. It's going to take all that information and it's going to process it through the rest of the radio, just like it did with your analog signal, your audio signal, excuse me. If you guys want to follow along in your TOs like I asked you to do, you can go to paragraph 3.2.2 and 3.3.2.4. We're going to talk about transmit clear voice signal flow in CC and CT next. And then from there, we're going to go to paragraph 3.3.1.6, and we're going to talk about transmit clear data flow in CC and CT. So data and voice was the key there. We'll first talk about voice. As voice comes in, it comes in as our analog signal through J1, goes to the ALC, automatic level control, gets cleaned up, so those varying voice levels are constant. Goes to the AIC, the analog interface chip. From the analog interface chip, it gets digitized. And sent through the rest of the radio. I apologize, I had to plug my headphones in there. For there, it goes to the VDP, which is responsible for enhancing and cleaning up that audio. Even if it's encrypted, it's still going to do all of these things. The only difference here really now is we've got it selected in CT or CC mode on the front function switch that we have of our radio. If we have it in CC mode, note that it stays inside of this A2, A4 here, and goes from there to the Citadel cover and to the CT-FPGA, which is the ciphertext field programmable gate array, and then out through the BIOP, the black input-output processor. This maintains and controls system status and functions for the radio, and then from there it goes to the CT data, goes to the modem, because it's data, and encryption in general has to go through the modem. I don't know if one of y'all asked me this in this class, I think it was last night somebody asked, but it does have to go through the modem if it's encrypted. It has to modulate, demodulate that signal. That's just something they designed. It has to do that because there is encryption in it. From PTFPGA, if we were still in audio and we wanted to go to CT mode, we would go back here, go to ciphertext. Now note that the A2A5 is its own separate subassembly. If something is outside of these dotted lines here, as you guys see, if you remember my kindergarten example earlier, you don't cut it out. So it's its own separate thing, its own separate subassembly if we're in CT mode. From there, it goes to the CTFPGA, just like Citadel cover did. From there, it goes to the BIOP. The BIOP is the black input-output processor. Again, maintains control system status function for the radio. And then the CT data, or voice, will also again go through the modem and to the CDSP. If it's data, it's going to take the exact same two paths that the audio took right here, except it's going to come in from J3. Any questions on that? Pretty straightforward?
Yes, sir.
Excellent. Let's move on. Next, we're going to talk about receive. Paragraph 3.3.1.2 in y'all's TOs. What are 3 things that you guys notice are different from the slide here? No response. Nobody sees anything different.
The antenna's in the front.
Thank you. The antenna's in the front. We have this thing called a notch filter here. And how about the entire circuit is reversed? So the top and bottom modules are swapped, the handset and the antenna are swapped, and each module's components are reversed and has a notch filter. When we come through, we go to the antenna coupler. If you'll notice, it does impedance matching, just like it did before. The directional coupler does that VisWAR, just like it did before. The high-level limiter, still limiting those high levels, that VisWAR from getting through the circuitry, same thing. Really big difference here is this pre-selector network is what it's called now, but however, we're still going to use how many out of 9 filters? How many filters are you guys going to use out of 9? Nobody?
Are we going to use 7?
You're going to use 7 of your 9 filters?
Or,
1.
Nope.
Is it just 1?
Nope.
Okay.
So remember in the previous slide, we'll go back here since you guys didn't pick that up. We will always use 2 of the 9 filters, regardless if we're in transmit or receive. And if you look at this, I can trace this out for you also, it actually makes sense. If you come through here and trace this just like I'm doing, if you got some colored pencils or whatever, if you're going to do band 1, you come up through here, we use that 1 filter, go down, come all the way around, go along our line. Let's say we were on band 7, like you guys told me earlier. I'm going to go down to band 7, come through, and then go out through this way. You guys see what's happening here? How the
Yes,
signal
sir.
travels? Comes out, goes through, goes out the antenna. Make sense?
Yes, sir. And then the second filter would be before the high level peak.
Yes, the second filter is going to be before the high level or peak limiter. In receive, it's called a high level or peak limiter because it's happening beforehand. The high level limiter here, it's happening beforehand.
Okay.
That's all. And then we have this new thing called a notch filter. The notch filter's job is to improve weak signal performance. If our signal is coming in below this 140 megahertz range because it just got pushed through all of these filters and shot through space and stuff, this is why. It just bounced off the ionosphere and we need to boost it back up to what it needs to be so we can get back to the original signal we had and understand the voice being transmitted. From there, we go to the low-pass filter again, and our digital attenuators. You will note this time that we have something called AGC in receive instead of TGC, but it's pretty much the same thing that TGC was doing, which what does TGC do?
Transmit gain control.
What does it do?
It adjusts the dB.
No. It adjusts the varying voice levels coming in for the antenna. It holds those varying voice levels constant for the antenna. So the AGC is going to hold those varying voice levels constant for the handset, the thing you're going to listen on. So then we go to this mixer here. If you guys will notice, our first IF in receive is 140.4 megahertz. What was our first IF in transmit?
The 140.4.
Negative. It was not. The first IF in transmit is 240 kilohertz. The second IF in transmit is 140.4 megahertz. Now that we're in receive, and I told you everything was reversed, it makes sense that we flip them around. And you can even see that on this diagram right here on this slide I have pulled in front of you all. There's the 240 kilohertz over here. That's our second IF. And then our first IF is right here. You guys see that?
Yes, sir.
Okay. But this first IF is actually produced out of this mixer here. From here, it mixes with 140.16 megahertz local oscillator 2 generated second IF of 240 kilohertz. Again, this is our injection frequency. And then the 240 kilohertz is then routed through the low power filter, amplified, and then filtered by a bandpass filter. When we come back down through here, we're going to go to our A2, A1 again. From there, it's going to do digital demodulation because we did digital what on the way through?
Modulate.
Digital modulation on the way through. Very good. So the signal enters the A/D converter before being demodulated at the DIF ASIC, digital intermediate frequency, application specific integrated circuit, and the output is going to be intelligence. What is intelligence? What two things can I send with the radio that you all know of?
Audio and
Audio and data.
Data.
Audio and data. Very good. Okay, from here, if it was encrypted, it would go through this top part. I'll point this out to you all now. And it would go to the modem. Even if it was audio, it'd still have to go through there. So whether it's audio or encrypted data, it will go through this modem and go up this way. But since we're talking about audio right now, it does not. From there, it goes to the biop. What does the biop do again? Y'all remember what the biop does?
No, sir.
Maintains and controls system status function for the radio. That's our black input-output processor. It's going to process that encrypted data or audio and pass it along to its decryption devices at this point because we're decrypting on the receive side. So either the Citadel cover or the embedded crypto assembly, depending on if you were in CT mode or CC mode. Make sense?
Yes, sir.
Okay. From there, the signal is then converted to the analog audio signal, and it is finally sent to the J1 connector. One of my biggest questions, before we all kind of wrap it up here a little bit, is what do you guys notice immediately is missing from here? What's missing that we had on the transmit side?
ALC.
The ALC. And what was the ALC's job?
The ALC, it smoothed out the signal.
Okay, it's the automatic level control. And remember, it's just that varying voice levels coming in. So why do you think we don't need an ALC on the receive side?
Because it's already leveled since it was going through the other end.
No.
Because we're receiving it.
What can you do with the volume if you can't hear somebody?
You
You can just adjust it.
You can adjust it yourself. If you can't hear them, you don't need an ALC. You can turn the volume up. All right, very good. This is what we talked about in summary, guys. We went from the antenna to the A1 to A3, A5. You'll note that this slide is blank because they want you guys to understand that everything is pretty much the same coming back through on the receive side. The only real difference here would be we have a notch filter here. So we had a notch filter there. Everything was reversed. We started with the antenna versus starting with the handset right here. Now, if you were coming through, and just like we did before, if you want to talk about the receive clear data signal flow, you'll notice it starts right down here because nothing changed, right? Coming through our analog RF sections up here. Nothing was different.
Right.
Cool. So go back through the CFPGA, go to the PTFPGA, our traffic caught, go to the DTE interface, data terminal interface, or data terminal equipment interface, go to the A1 chassis assembly, and then go right back out into the data into your computer. If it's encrypted, it's going to do this path I showed you a minute ago. Going to come through the modem, go through the BIOP, the black input output processor, go to the CTFPGA. From there, go to A2, A5, then go to PTFPGA, come out and go through, and if it's audio encrypted, it'll go there. And if it's data encrypted, it'll come down here like we said before. Now, one thing to note, and I don't know if I explained this when I was coming through the first time, is our signal is considered either red or black if it's encrypted or unencrypted. This is saying the red to black interface right here. You guys may see this differently at your other bases that you go to. It may be black or red, depending on what it is. SIPR lines are typically red. NIPRNet, which is your unclassed lines, are typically green, and then you have some other colors for your other various networks. So just something to note. Just get with your ComSec again, like we were telling you guys to do earlier, and talk to them about what their local guidance is and what they have for the colors of cables and things like that. I've heard that especially in overseas locations, they like to use different colors as well. So just make sure you understand what they're talking about. So where does the analog to digital conversion take place here?
It takes place at like the beginning, so it can transfer into data more quickly.
What assembly or subassembly?
A2, A1.
A2, A1. Okay, so if we're talking about the receive side though, where does analog to digital conversion take place? So if I change this question to say, where does analog to digital conversion take place on receive, what are you going to tell me?
A2 lower chassis assembly?
Yeah, A2 lower chassis assembly, A2, A1 specifically. I think somebody just said it a second ago.
Yes, sir.
Yep. And what is the frequency of the second IF? Remember, this is receive now.
240.
240, very good. 240 kilohertz, outstanding. What is the difference between TGC and AGC?
TGC is for the signal going out, and then EGC is for the handset.
Yeah, very good. So TGC is for the signal going out, the varying voice levels going out to the antenna. That's awesome. And the AGC is for the varying voice levels coming into the handset. Outstanding. Very good. How many filters must be selected? I don't think anyone's going to get this one wrong.
2.
Two,
Of?
sir.
2 of?
2 of 9.
2 of 9. What is the difference between CC and CT? Which one do we share with NATO and allies, and which one do we not share?
I assume we share CC with them.
Very good.
And we don't share
the CC.
CT.
Yep, we share the CC. We do not share the CT. CT is the type 1 DoD encryption that we keep with ourselves. CC is that encryption that we share, and it's loaded from the front panel. Very good. Y'all crushed it. Any questions? Let me stop this recording.